Rainbow Six Siege is a tactical shooter famed for its realistic combat and mechanics. In terms of throwables, however, we're going to be using physics to see whether or not Siege actually lives up to its reputation. Frag grenades and C4 in particular seem to be likely candidates for critique, as an attacking operator can throw a grenade about halfway to Africa, while throwing a C4 in defense feels like you're trying to toss on that ingot. So I got together with one of my friends, and we went to the Air Force One map, since it has fairly long, straight hauls, and would make it easy for us to measure our throws. I took Sledge with frags, and he took Capcan with C4, and we got to work. So we had each person set in their reticles, so we were throwing from about the same elevation angle, and then throw our respective projectiles. Using Capcan as a measuring stick, we found that Capcan threw the C4 2.5 times his body height, and Sledge hit that fastball special on the frag and threw it 7 2/3 Capcans away. Capcan, according to in-game statistics, is 1.8 meters tall. I then googled the stats for both the military-grade block of C4 and the average frag grenade, tacking on the way to my home phone to the C4, since the in-game model of the C4 has one duct tape to the front. Using these kinematic equations, as well as the given variables, and ignoring wind resistance, we can find the force with which the operators throw their respective projectiles. The times for throwing were measured for the videos of the animation. So first we find the x-components of both the projectile's velocity, then using the time for throwing to calculate the acceleration, and finally Newton's second law for the force exerted. And as one can see, it's evident that the operators throw drastically different forces. Obviously, this part of Rainbow Six is not realistic due to balancing issues, given an operator able to yeet a C4 into an attacker spawn directly after a round starts would be terrifying and completely overpowered.
Okay, first things first, we need a ruler to measure things in the game. Mario's cannon height is 1.55 meters, so we'll just use that for simplicity's sake. This is an area on stage 1, where we can see Mario standing next to blocks. From this, we can determine the dimensions of the blocks are 0.775 meters by 0.775 by 0.775. If we take a few practice jumps, we can see why Mario's middle name is Jumpman. He's jumping 3.1 meters in the air, which is almost double the world record box jump, set by Evan Unger in 2018. Mario jumps, he covers 0.775 meters in 1/3 of a second. When he comes in contact with the block, he slows down in 5/100ths of a second. Using this information, we can determine the force being exerted on Mario's hand when he comes in contact with the block. The equation for velocity is distance traveled divided by the time it took to travel that distance. In this case, Mario traveled 0.775 meters in 1/3 of a second, which gives us a velocity of 2.32 meters per second. The equation for acceleration is the change in velocity, which is negative 2.32 meters per second, divided by the time it took for the velocity to change, 0.05 seconds. When we do this, we get negative 46.4 meters per second squared. To find the force, we multiply the mass that is decelerating by the deceleration, which in this case gives us negative 4,547 newtons. This force can easily break a human femur, which is the strongest bone in the human body. So it would basically shatter Mario's entire hand and probably also arm. So after Mario hits his first block, he's probably not going to be able to run at the end of the level, let alone defeat Bowser.
I decided to analyze the physics of Overwatch. I calculated the force required for Roadhog to be able to pull in another Roadhog with his hook. I first tested how far he is able to toss his hook. I found that he's able to throw it 20 meters. Then I needed to figure out how much Roadhog weighed. From an official Overwatch video, we can see his weight is 550 pounds, or about 249.84 kilograms. Next, all I have to do is calculate the acceleration of the pull-in. From this clip here, I was able to calculate the velocity to be about 40.984 meters per second. To do this, I used a stopwatch and timed how long it took for him to pull in his target. I did 10 calculations, then took the average of them. Then by using the average time, I was able to figure out the velocity and acceleration. From these, I was able to figure out the force Roadhog uses to hook another Roadhog.